Today we are going to address the problem of outdoor and aerial semantic navigations, as you can see in this kind of videos, in which the robot's goal is to find arbitrary goal objects descripted in natural language in unknown outdoor environments, such as finding water tower in this kind of field or finding tunnel entrances in this outdoor neighborhood environments. There are some fundamental challenges of outdoor and aerial semantic navigations as opposed to indoor semantic navigations. First, there's very large scale and large spatial horizon, which requires long-range semantic search. And secondly, the semantic cues are very sparsely distributed, and there's lack of hierarchical structures, which is not available in outdoor environments as opposed to indoors. And I think that long horizon decision making requires persistent spatial semantic memory. There are some lines of work that uses LLM to just generate actions. Although those LLMs are quite powerful in semantic reasonings, they are fundamentally generating short-sighted behaviors because they are fundamentally reactive to the current or recent observations. Our approach is different. We believe that usage of construction and maintaining of memory or spatially and semantically grounded map can support downstream action and planning for long horizon decision making. What I mean by spatial and semantic representation is that given images, robots can first reconstruct weak structures using LiDAR or depth sensors, and then we can project visual language features onto the 3D representation using different kind of visual function models, and then we can compute the cosine similarity between the features of the latent features in the 3D and the text features later. And since we are addressing outdoor environments, we want to extend semantic representation beyond the sensor's frontier. For example, if the objects are within the depth range, we can construct voxels. But what about those objects that are far beyond the sensors or far beyond the depth coverage? The key insight is that complementing these semantic voxels, we encode such information into a second representation called semantic rays or semantic ray frontiers. You can think that semantic voxels are there for within range objects, and semantic rays are there for beyond range cues. In our previous work in ray fronts, which was published last year, we constructed semantic ray frontiers as a complement to semantic voxels. Not only maintaining semantic voxels and projecting semantic features onto the voxels, but we maintain the frontiers as well as the direction-based representation of semantic rays and projected semantic latent features on top of that semantic ray fronts as well, as you can see in this video. The key points of this semantic voxel and semantic rays are that they are open set or open vocabulary. Given any types of query like this image or very arbitrary text like road cracks or trees or radio tower, it highlights the voxels or rays that has higher cosine similarity between the text features and the latent features that are stored in semantic voxels or rays. In this work in ICRA, Raven, we use this ray fonts as a persistent spatial and semantic memory. Given image, depth, and pose, we construct semantic voxels and semantic frontiers on top of our mapping representations. And using that, we adopt behavior tree-based framework in which it adapts the behaviors depending on the context and situation of the environments. For example, for the short-range semantic cues, it triggers short-sighted semantic voxel-based search, which is very, very good for short-range and precise localization of the objects in the close range. For example, finding ships on the house in this kind of environments. If such things fail, we want to trigger the long-range semantic search, which is based on the ray representation. As you can see in this video, the rays encode long-range cues such as water towers and those direction-based informations. As you can see also in this video, it shows two different directions pointing out two different objects, blue tarps in this environment. And I think that 3D semantic voxel and map representations can serve as a persistent memory because it can incrementally and continuously save information to the representations and does not forget the information even if the new observation comes through. And importantly, when a new task or goal is introduced in the middle of the task, it does not need to rebuild the representation, just retrieving the previously built representation suffices. For example, let's say that the first mission is to go to the radio tower first. As you can see, the robot is heading towards the radio tower, which is highlighted with the yellow color. And then let's assume that their second task are given in the middle of the mission. For example, let's say that the second task is finding the bridge. And the robot does not have to re-find the bridge because it has already seen that object before. And just by performing cosine similarity search using the voxels and rays, it can instantaneously change its direction and go back to the bridge. using these representations. What if both semantic voxel-based search and semantic ray-based search fail? In this case, we adopt the auxiliary search using LVLM guided search, in which use internal availability to be as a VLM. And for example, the LVLM suggests going to the related objects or related areas first if it is really hard to find. For example, in this video, the LVLM suggests go to the park first, go to find fountain, and then going to the park, the robot uses ray search to go to the fountain. We tested our method Raven in 10 different simulated environments with 100 different semantic tasks. And this is one of the examples of task, which is finding fuel tanks. We compared our method as opposed to different baselines, such as LVLM-based method, which shows very meandering and unsuccessful paths. VLFM is another map-based work, but it's not as good as our methods. As you can see in this final snapshots, our method Raven shows successful trajectory that can find both fuel tanks environments. These are the quantitative results where our method shows higher performance than previous baselines, as well as showing that our methods are, the second table is the evaluation results, where it shows our semantic voxels, rays, and LVLMs are all important components of our method. As for the real robot experiments, we customized our payloads by attaching ZX camera and using NVIDIA Jetson Green AGX payloads, and ran real experiments in outdoor field site. The task is to go to the red building first, and then robot starts with frontier-based exploration or random search at first. But by the time it discovers red building, at that moment, it instantaneously catches that and stores that information into the semantic rays and changes its direction and goes towards the red building, as you can see in this video. Okay, finally, we just released our code, in which we provided simulations and datasets and annotations for outdoor semantic navigation benchmark. If you're interested, please look at our papers and code. Thank you so much, and I'll take questions.
Okay, thank you. We have time for one quick question, perhaps. Anyone in the audience would like to ask? Oh, yeah. Go ahead.
Thanks for your presentation. I wanted to ask about the size of the map. So when we are having the clip embeddings, they are quite big in a dimension space, and how you optimize the overall map for clustering and everything?
Yes. Since we are dealing with the outdoor environments, in terms of the memory or the map size, we were able to maintain the size of the memory by choosing more sparse sized voxel, which is 0.5 meters per each cube. And as you said, the features of VLM models, which is split, in this case we used a model called Radio or RADSEC, which uses like 768 feature dimensions, which is a lot, very big. But we were able to run this on board using NVIDIA or AGX. But one limitation is that our memory representation goes linearly with the scales and linearly with the times, and that's one of the limitations that we have to address in the future.
Okay, thank you very much. Just to check, one more question possibly? No? Okay, I think we will thank the speaker one more time.